Yep.
Hey everybody, I recognise some faces, I see some new faces. For those of you who don't know me, my name's Andy Kellogg. I'm a scientist at IBM. I'm the lead judge for the bridge competitions. This will be my 22nd MESA day doing bridges. So I've seen it all, and although every year you think you've seen it all, then you always see something new. So good news, how many of you have done the bridges before? Any sort of bridge? Okay, so that's about 2/3 of you, that's good. This is a good year to be doing the bridges. I downloaded the new rules today, and I found out they finally eliminated one of the little funny things in that there used to be two different sorts of mineral mechanics. One for 7th and 8th grade and one for 6th grade, and the dimensions were slightly different between them, and it was really confusing for everybody. So now there's just one mineral mechanics for all grade levels. And it looks like they've also now pulled in stick together. So 7th and 8th grade were doing mineral mechanics last year. Now they're doing craft stick. Together. So if you're doing, so we've got teachers here from 6th, 7th and 8th grade? Yes. Good, alright, so I'll do it in grade order. So I'll start with those, I'll do the mineral mechanics for the middle schools, and I'll do the high school also with bridges at the end. So we've got 45 minutes, I'll do about 15 minutes on each of the rules. So I looked through the rules, and the good news is there's nothing else that's changed in all the rules except just those things about the lack of change in dimensions. So, so these will be the rules that we'll be using. Run 3 teams, up to 3 teams per center, 1 or 2 students per team, so that students will be individuals, or they can have 2 on the team. And the idea for all of the bridge competitions is what they're going to be doing is building a bridge to span a certain distance, and then they're trying to build the strongest bridge using your supplied materials, and then we'll be testing it. And we test it by loading up with a 2-ton hydraulic jack, and we basically load up the bridge until we have a catastrophic failure. The craft stick bridges usually go pretty good. The best ones are like in the 300-pound range, which is pretty good. You know, a couple of adults can stand on these bridges. Mineral mechanics will be a little lighter, maybe in the somewhere between the 1 and 20 pound, and then the balsa wood's also pretty strong, also in the 300-pound range. So the only materials that you can use are craft sticks or popsicle sticks, which have these dimensions: 4.5 long and 3/8 inch wide and 1 16-inch thick. With this type of bridge, you're limited to 200 sticks, or partial sticks too. So if you break a stick in half, that's suddenly 2 sticks. Okay. So you want to tell the kids, although the weight is the same, you know, there is actually a weight thing in this one as well. But what we do is we don't actually have time on MESA Day to actually count all the sticks in the bridge. So what we do is we know how much one stick weighs, we weigh the bridge, and then we kind of do the math and see if it's close to being 200. If it's going to have like 205 sticks, we're not going to pick it up. You know, but if it's got 300, we'll notice it. So basically, tell your kids, you know, try to keep it within that 200 stick limit. And the only glue that you can use is the water-soluble Elmer's glue, the white one. Elmer's now has a stronger glue, Carpenter's glue, I think, which is a yellow glue. So don't use that. We can see that when it dries to a sort of a dingy yellow beige colour, whereas the Elmer's dries perfectly clear, so we can dry it. So here are the dimensions for the bridge. Actually, let me pop down to the picture. Yeah, so this is basically what our test stand's going to look like. It's made of 2x4s. We have some vertical supports here. So these 3 pieces of the test stand. They're spaced 14 inches apart, and then the students have to build a bridge that spans this. Then we put our testing apparatus on the top there, and we load it up there, and then we see when it breaks. And so the dimensions are here. I won't go through them all in great detail, but we have a maximum length, maximum width. This is the only sort of bridge bridge type we need a roadway, and the other 2 bridge types don't need a roadway, but this one does. And so you have limitations on the roadway. Also, what's unique about the popsicle stick bridges is the type of construction you can use is unique to the bridge type. Let's see, some other rules. It has to be labelled. Make sure there's a label on the bridge. There's no kits allowed. I haven't seen a kit out there. I don't think I'd recognise one if I saw one. So just take some popsicle sticks and build the bridge. This is one of the most confusing rules. This is his 50% rule. So what that says is, we'll just assume that this is a popsicle stick. So it says that a maximum of 50% of the craft stick's total flat surface may be glued. So what that means is, so the craft stick has a top, has a bottom, and then has an edge around it. The edge is not included in that rule, in the 50% rule. But what it says is, so because you've got the stick with a top and a bottom surface, 50% of the stick's flat surface is on the top, and the other 50% of course is on the bottom. So that's 100% of the total stick's flat surface. And so if you take another stick and you glue it on there, so that the top of the stick is totally glued and covered by another stick, then that's it. You've glued 50% of the flat surface. You can't glue anything else. So if anything is attached to the bottom of the stick, you've just broken the 50% rule. Okay?
Try the whiteboard on
Sure. So let's do it this way. So now we're looking down on top of a popsicle stick. So here's the top of it. If I bring another popsicle stick on, actually let's look at it from the side, might be easier to see. So let's say I have 3 popsicle sticks. And that's badly drawn, but this is meant to be halfway on each one. So the top stick, the bottom surface is totally glued, 50% to this stick and 50% to this stick. So you can't attach anything to the top of this stick here. So if there's another little stick that comes down and gets glued on here, that's not good.
But you could glue it onto the side and that would still be okay.
You could, but it would be a really weak joint because
Right.
the stick is very thin, but that's okay, yeah. But yeah, just in principle, that's true.
Okay.
The bottom 2 sticks, now, this stick has half of its stick glued to this one and half to that one. So you can actually attach something else to here because even though it's 50% of the bottom surface, there's another 100% there. So this 50% actually only represents 25% of the total surface. Okay. So you can still continue to glue more on here, or you can glue something on this one, and that's okay. So we don't really go through and look at all the sticks to make sure that they're all, exactly 50%. But what you want to avoid is having sticks that are like this, where there's 2 sticks totally glued on top of each other like that.
Lamination.
Lamination, exactly. That's what we call lamination. Because then, now that both these sticks have 50% of their surface is glued, you can't attach it to anything else. So these pair will just be floating in space. They can't be attached to anything, unless, as you said, you attach to the edge. But that would be very weak. Okay. So that's the 50% rule, and then you can do the math with other things. 25, 75, 33, 66. You kind of get the idea. But and then again, that's eyeballing too. So if we have a stick that's like this, and we bring one down, and this one is attached 50%. So this is actually 25% of this red stick. Because there's 50, there's 25, there's the other 25. You can actually glue one here and have half of that. So there's still a little bit left, so you can actually do the rest of that with another stick there. So we have to look at each stick and say, okay, well but then we don't usually use a rule, we usually just eyeball it. So what you want to tell your kids is don't make us think that it is. Don't make it look close enough that it actually might be, actually disqualified. Okay. Is that so? Is the 50% rule clear?
Mm-hmm.
Yeah. On this glue again. No coatings on the bridges. So when the bridge is built, you can't coat it with anything. Don't paint it. Don't use hairspray, like some kids have done in the past. And also that applies to the glue too. So you want to make sure that tell the kids to build a nice, neat bridge, and only use glue in the joints. And I know in the past, there's not a lot of excess glue in the bridge, and the kids just paint it all over the bridge, thinking just to get rid of the glue. But that actually makes it a little stronger, and it also breaks that rule that the bridge isn't supposed to be painted with it. So it's better to tell them just to take a damp sponge and wipe the glue off, the excess glue off. Don't let it leave it more and dry. We also noticed too in the past, a lot of the kids, they use newspaper. They want to protect their parents' table, so they build it on a newspaper. And then of course the paper and wood are the same thing. So when the glue's dry, you go to lift it off, the paper's stuck and they tear it off and there's little strips of newspaper everywhere. But we can see it's not an obvious attempt to try and strengthen the bridge, it's just how they made it. So that's okay. So tell them not to fret too much if they bring the bridge, and there's little bits of newspaper everywhere, that's okay. Bridge has to be open at the top to allow, see this bridge is a different sort of bridge style. There's no picture there. So, you know what, I'll grab the picture now, because I think everything else is the same. Oh, no, one more vital difference too with this type of bridge is because of the roadway, not there. over here. I-beams are illegal. What an I-beam is something that looks like this. If you look at a typical girder that you'd use in construction, which looks something like this, I think. That's what we make our buildings and bridges from in the real world. You know, it's 3 pieces of steel that are welded together like this, very strong. And that's, if you look at it from this direction, that's why it looks like the capital letter I. So that's what we call an I-beam, where there's 3 sticks glued together, you know, on the edges. And even though that's great on a real bridge, we don't want that in these sort of bridges because the bridges are already getting to 300 pounds. And if we used I-beams, then we wouldn't be able to, we'd break our test apparatus. Our limit on our scale is 450 pounds. So that's the main reason that the I-beams are illegal. But T-sections are okay. So if we take away one of those sticks and make it look like a T, that's okay. And on the roadway is special compared to the rest of the bridge in that you can actually build sticks. We actually encourage that you actually use the sticks like this, looking down from the top now, and all the sticks are actually glued along those edges. And so this would be the roadway, because you have to have a smooth, continuous roadway for traffic to come on. And I think in previous years, I don't see it here, in previous years they always said that you could bring like a Hot Wheels car or some little toy car and just, you know, as long as the car can roll across one end of the bridge to the other, then that's a continuous roadway. Because in the past, some kids have I guess they're kind of fighting the 200 stick rule, and so the roadway isn't continuous, it looks more like a ladder laid down, and that would be a continuous roadway. But this style of bridge must have a continuous roadway. And so on the roadway, it's the only place where you can do this horizontal lamination that we would call, where you can glue the sticks right next to each other. But then, of course, because those sticks are all glued on their edges and they're extremely thin, then this whole structure is very weak. So you want to reinforce it underneath, looking down from the edge of the bridge. And this is where you would use these other sticks that would actually come under here to support the roadway from underneath. And then if you look at those from the end, that's why they look like this T-section. Okay? But then tell the students, don't be tempted to put another layer of sticks underneath there, and then that makes the T into an I, and then that's going to be illegal. And that's it for the rules. So let me actually do this. I'll get back to main screen. Escape, maybe? Escape, and then, so these are the roadways that I was talking about on these bridges. This bridge doesn't have a roadway, so this one would be disqualified because it doesn't have the roadway. Neither does that one there. And you can also see that these bridges are very long and spindly, they don't look very strong, so they wouldn't have tested very much anyway. Underneath the roadway here, you can actually see there's some sticks going this way. These are the T-sections we were just talking about, and then they've got these other supports hanging underneath. But there are restrictions in the rules about how deep this can be. It's 3.5 inches below the roadway, and 7 below the roadway, 3.5 above the roadway. So make sure you read the rules, make sure they're okay. And then also there has to be a space underneath the roadway for our test stand, our vertical test blocks. So what often happens is the students build these structures under here, but they don't follow the dimensions exactly, and we can't fit it on our test stand. And so if it doesn't fit on the test stand, we can't test it. So the best way you can do that is you have access to some wood. You can build your own test stand that looks just like ours, just some 2x4s. With the vertical parts spaced 14 inches with 3.5 inches high, just as you see in the rules there.
Click.
Here's some more. And here's an interesting looking bridge. Looks like a stack of pancakes. And as you can see, they tried to make the feet strong, which is a good idea, but then the middle was kind of weak. And even though this looks like it might be illegal, actually it wasn't. It was okay. But it came out very heavy, and then when you do the strength to weight, it didn't actually come out very good. This one again has the nice roadway, but then you can see these pieces down the bottom here are kind of weak, so you may want to think about some ways of strengthening those. Here's a shot of one of the bridges on the test stand. So here's our 2x4s that are made to span there. You can see how the bridge is resting. So there's 3 little rows of cross sticks there holding the vertical supports, and then there's the roadway. So here's our test stand with the test plate. The test plate comes down the middle of the roadway there, and then we start loading it up. And also what's important here is that these 3 legs here are exactly flat and parallel, because otherwise if it's not on the test stand and if it starts to rock a little bit, that's when all the forces start to get asymmetric, and that's when the things start to fail. So the best thing for any of the bridges is you want to have, actually let me go back and start with a little bit of design principles. So all the bridges are going to have the same sort of testing, where we have the test stand. I'll do the bridge in a different colour. Whatever your bridge looks like, it's going to be some sort of box-shaped thing. And then we have our test plate goes on the top, and then we apply a load this way. And because of the forces are equal and opposite, when we apply a load this way, the bridge via the test stand pushes back this way. And because we're loading in one point there, and then the test stand is pushing back at 2 points, then the force is divided equally between these two. And so basically you can imagine a vector coming down from the applied force to each of the test stands pushing back. And so there's going to be this 50% partition between each of the legs of the test stand. So, and I'm saying that because your bridge has to be exactly symmetrical around that testing point. So if the left of your bridge doesn't look like the right of your bridge, then the structures on the left and the right are not going to respond to the forces equally, which is what you want. So the strongest bridge is going to be a symmetrical bridge. And whatever else is in there doesn't really matter. The most important thing is to make sure that everything on the left and the right is symmetrical. So you can imagine if you put a mirror here and put it that way, then what you see on both sides should be exactly the same. And that will be the strongest type of bridge, irregardless of what the design actually looks like. Because what happens is, one of the things with the cross sticks, and actually especially with the balsa wood sticks, is when the students start making typical box sections here where they use diagonal reinforcing or even cross reinforcings, then what happens is if these sticks aren't exactly the same length, if you look at it up close, then you'll see that these things might be up and down, a little higher over here, and then when you start to load it, then this is when you start to get this asymmetry in the forces coming to this test stand. And then what happens is it's just like standing on one leg. If you hold 500 pounds with 2 legs, you lift one leg, now suddenly I'm holding 500 pounds on one leg. So it's very different, right? So you want to make sure that everything is all balanced. We often see when we start to test the bridges, you'll start to see a rotation in some of the bridges. That rotation is a great indication that something wasn't symmetrical. And when it starts to rotate, then you actually start to get transverse forces coming in, and then it usually fails very quickly after that. And the strongest bridges, the bridges that we've tested at 300 and 400 pounds, have always been beautiful and symmetrical. Here's another nice example. There's the roadway, the discoloration here, that's the label. You can't see that at the end there with the school and the name. And underneath you can see there's a nice strong cross bracing here with 3 or 4 layers of sticks. And that's all legal, and then they've actually tied these sticks with some other pieces along here. And these sticks down here are only glued at the end, very short joint right there to its neighbour, and then the ends of those sticks, and that's all fine. That's all within that 50% rule, those sticks. And this is a good design because when the test stand comes up under here, there's a lot of structure to actually channel the force from the top of the bridge to the ends of the bridge, and it's tied up in the middle as well. So these are good, strong sort of designs. There's another nice one. Looks very similar to the previous one, except this one they've actually made it bend down a little bit. I'm not sure that does anything for the strength of the bridge, but it does change the appearance of the bridge. Don't forget there's also, not only is there strength to weight, but there's also the creativity and craftsmanship. So if everybody's bringing rectangular, square bridges and someone brings something like that, it's going to get the judge's attention. They go, hey, this is a nice design. It looks a little different. One year somebody actually built a bridge that was a beautiful arch bridge, looked just like that. The bridge in the Friendship Gardens in San Jose there. And very, very nice designs that can come up. There's no variation on the theme. This one, is this a strong bridge?
No.
No, no. Because it's just got these little vertical sticks and they're going to snap and they're not joined to their neighbours. It would have been better to take a lot of these sticks out and make sure these vertical ones were all joined to their neighbours, right, so they're stronger. So this is, your job as an advisor is to help the kids understand, what's going to happen to the bridge and the forces involved, and even though this might look like a nice bridge to them, it's not strong. Another selection of bridges here. Yeah, so here's some where there's one of the rules that says there has to be a clear and unobstructed access to the roadway, because we're supposed to put the test plate on the roadway. So see this bridge here, the roadway is down here, and then we can't get the test plate through the structure because of these diagonal braces across here. So what we have to do with this one, we have to put the plate there and test it, and then of course this part's going to break off, and then we put it on the bridge mill, so we have to test it twice. So that's kind of a bit of a waste there, where other ones like this, they've left it open so we can actually put the test piece all the way through. I think I'll stop there for the I'll move on to the next one.
Huge structured things, and they just explode on video. It's just so fun to watch. Then they get jazzed up.
Yeah, drive past is cool. It's very brutal. So the Baltimore bridges are the nicest looking bridges, I think, in our competition. And you get some really nice looking structures that actually start to look like real suspension bridges. So this is a very nice one. And one thing I'd like to call your attention on this one is notice the symmetry. Look at the left of the bridge. There's the middle of the bridge, the left and the right. Very, very symmetrical. This is a very nice bridge. And one thing that we've always seen in the past is, actually it's a golden rule always, is the bridges that win creativity and craftsmanship always win strength to weight. And the reason is because a symmetrical bridge is usually a neat bridge. It's a nice looking bridge. Everyone looks at it and goes, ooh, that's a nice bridge. And because it's symmetrical, it's very strong. You can also see they've done a lot with the, this is where the bridge is going to sit on the test stands. They've got some nice diagonal members taking that force from the test plate down to the legs. And there's lots of little support structures to make sure that's a nice strong connection. So this is good. Here's a variation on the theme. This is kind of like a skinny bridge. This bridge reminds me of those moving billboards they have on trucks, right? But this is fine. There's nothing to say the bridge has to be big and wide. And so what they've done is, instead of making the bridge unnecessarily wide, they've made it narrower, and they've used, now they've got triple strength here, right, instead of just a single beam or a double beam. So this is good. So you want to start getting your students thinking about that too. Don't make a bridge that looks like everybody else's bridge. Think about where you've got a budget with this bridge. 95 grams is how much balsa wood you can use. So you have to put your wood where it's going to do the best job in resisting the load from the test plate. So this one is very well thought out. It's like, well, the plate's going to go here. We want to transmit the force to the legs, and then we'll make the rest of kind of look like a bridge. And because these are very long and skinny, so they're very weak inherently. So you have to try and reinforce them at various points. You could also put more pieces in here and try and reinforce this. So this is a nice sort of style. And there is a minimum of how wide the bridge can be, but they made the minimum, but they didn't go to the maximum. And so they used their wood budget very carefully to go for strength rather than width.
Which is strength to weight, right?
It is strength to weight, yeah.
So if you did 95 grams of wood on a scale, how much would the glue add to it, do you think? About 10%?
Oh, well, I misspoke. It's actually 95 grams constructed. Right. So that includes the glue.
And the tag.
The tag is minimal. And actually,
it just adds all up.
You laugh at it. Actually, what we've done on some days is if it's 96 grams, we take the label off and weigh it again, just to make sure it's not the label.
So the glue would add another 10, 15?
The glue is typically about 20% of the weight. Yeah, because balsa is very light. The craft stick is less. but the balsa is very porous and very light. And so the wood actually becomes a big percentage of the total mass. Yeah. Here's another nice bridge, more of an open structure, but again, notice the symmetry. Beautiful bridge. And they've got the same sort of structure. You know, they've got a strong thing here with some diagonals going down there. And then they put some cross pieces in to try and strengthen all these pieces here, which is good. And don't forget, like these corners here, they're really not involved in the crushing, because you know, the forces go this way, and anything that's sitting out here in this area is usually not supporting this unless it's tied to the pieces that are going to get broken. So you can imagine that as the forces start to get applied here, you've got some pieces coming down here, and so we've got a compression force coming down on this one. And so what's going to happen to this is it's going to start to move around, and it's going to like try and buckle into like an S shape or something like that. So you're going to need to have pieces on either side of it to try and resist that. Okay. So if anything that's here out on this side of the bridge is not strengthening anything that's here, all this is wasted, literally dead wood. Okay, because it's not being involved in the crushing. So it's adding to the weight without adding to the strength. So you can actually try and get the corners of the bridge, and you will see that in, I think, some of the pictures here. There's another nice symmetrical bridge. Again, very strong here in the middle, but the only problem with this one, what can you guys say about this one? Once again, we have these pieces coming in here. Look how long and skinny they are. And there's nothing to stop these ones from bowing or breaking. Right? There's no side reinforcing. So what you want to have, these are nice. You've got these nice strong legs, but as I just said, the leg part up here does not do very much. So take this wood from here and reinforce these pieces and make it strong.
And Dr. Kellogg, can I ask a question?
Yes.
I had the question once about the wood being penetrated in water in order to bend. What is your ruling on that?
Oh yeah, that's fine. There's nothing in the rules that says you can't do that. And some students actually did it a couple of years ago, and they made a beautiful bow bridge.
Oh.
And
Woodworking.
yeah, woodworking it. Yeah, so they soaked it until the fibers got, and then they gently bent it and let it dry, and then it stays in that position. That would pre-stress the fibers to a certain, it kind of bends the fibers, and usually that strengthens them. So that's a possibility as well.
What about getting liberal with the glue all over the member?
No excess glue on the bridge. That's one of the rules.
Just at the joints.
It's at the joints.
Connection spots.
At the connection spots is fine. If the whole bridge looks like it's been dipped in Elmer's and then dried, you can see it actually. When after Elmer's dries, there's a little bit of a sheen to it, so we can actually tell. And again, given the mass of the glue and everything, it would actually increase the. I'm not sure the added strength from the extra glue would help the weight. What's wrong with this one?
There's not a runway?
It doesn't need a roadway, no, not for the balsas.
It's not symmetrical.
But it needs to have supports. It needs to have it needs to have two legs and then a cross piece. It's just got the cross piece, so it doesn't suit the rules there. There's another one with nice strong legs, but again very weak. They've got these pieces here, which isn't too bad. But look, we've got a test plate here. This part's just going to snap right there. There's nothing pushing back against the test plate there. So.
You're saying there's a minimum height?
There is.
It's got to have legs.
And it's got to have legs. Yeah, it's got to look basically this sort of shape, like an inverted C. This one's nice. It's all very, Venetian blindish looking. Looks nice. But again, it doesn't have anything. This part looks strong, but then this part attached to here is very weak, and it's only through here. And so when you start to crush this bridge is going to start to go like this, and then it's going to start to lift off the test stand, and then just going to break there. So I would put more diagonal bracing in or something like this. There's another one that's nice. Looks strong here. They've thought about the test plate here. That's nice, but again, missing some diagonals here. There's another nice one. They haven't bent the bridge, but what they've done instead of making it straight, they've actually used shorter pieces and glued them and made this very strong. I remember this bridge. This was a very strong bridge.
Isn't that excess wood up in the corners, you said?
It is. It is. And I'm wondering if I actually have a picture of the one I'm talking about. This one? Here it is. So this is one that doesn't have, this is weak for other reasons, but it doesn't have the corners. So if your bridge actually looked like this, that would be perfectly fine. And actually that's preferable, so all the wood that would have gone there, you will put it back under here in some sort of testing. This one is very weak this way, and then put that in there, and then, you know, I think my time is just about up here. How many more pictures? Ah, what's wrong with this one?
No legs.
Well, it's not legs, but it's not a roadway. Does it need a roadway?
No.
No. This is a crafty bridge built with balsa wood. So unfortunately, this is not the student's fault. He didn't get any advice from you guys or from his parents, right?
Oh.
Because someone gave him the wrong rules. He was in the wrong grade, and he saw someone else's rules probably, and he was in high school, so he built his bridge using middle school rules. Wasted his time. I feel sorry for the kid because it wasn't his fault. You know.
Isn't that illegal wood too?
Absolutely. Yeah, this is totally illegal for balsa wood. There's all these laminations which are totally legal. And so, yeah, I feel sorry for the kid who put all his time into the bridge. And then last shot, there's a balsa bridge on the test stand. And as you can see from this bridge, see, once again, this is too much height. See how long and spindly all the legs are? Looks like a daddy long legs. You know, so it's not going to be very strong. So you can actually drop the height of the bridge, keep it within the dimensional restrictions of the rules, and take all this extra height and put it into strength. Okay? So if you don't have any other questions, I'll hand it over to the next competition. Here? Yep, couple. Alright, so we'll do this. So this time I'll start with the pictures first, then we'll go through the rules. So the mineral mechanics is different to both the craft stick and the balsa wood bridges in that you're not starting with wood, you're starting with paper. And even though they're the same sort of materials, paper is kind of the weaker form of wood, you know. And so from a judging point of view, or actually from a construction point of view, you want to approach it in a different manner. Because manila folders are inherently weak. And so what you have to do is you have to build a structure. You still have the same constraint. The test stand and the testing apparatus are still the same. You've got to build a bridge that spans a distance, and then we're going to load it up. But you're going to have to treat it differently because it's paper rather than wood. And so paper is very floppy this way. So if you bring a bridge that looks like this, it's just going to go buoyant. You know? And so we see a lot of the manila bridges that are very elastic when we test them. And so what you want to do is change the dynamic a little bit by making a structure like this. You roll the paper up, and then if you try and crush it this way, it's much stronger. So you want to get the students thinking in a totally different way that what you need to do when you do the manila bridges is you need to make a series of geometrical shapes and glue them together. Okay? So you can either roll up the paper like I showed you, and so looking down from the top, if you're spanning the test stand, you can do a whole bunch of cylinders together. This is what it looks like from the side. And then you glue the tops and bottoms with another piece of it, and that's basically what we're looking at here, where they've used some sort of triangle sort of, actually it looks like triangles they've glued together. So you can use cylinders, circular cylinders, you can do triangular cylinders, we'll do them this way, you can do squares. But the most important thing is that, while each cylinder may be hard to crush, we're not crushing one cylinder. So when we're on the test stand, what's actually happening, if we put the test stand here, test stand here, and then we put the plate down and we start crushing this way. There's nothing actually under this cylinder, so we're not really crushing that cylinder, are we? What we're doing is we're transferring the force to this cylinder, to that cylinder, to there. And so what usually happens, especially with this style, when you have a single sheet of manila doing some cylinders together, they usually end up just deforming like this. It kind of looks like a goofy green when it's done. That's what happens on the test stand. They all just bend down in the middle there, and then what usually happens is, the bad news about these rules is that they don't give you very much, the maximum length of the bridge is very close to the ends of the test stand. The size of the test stand and the size of the bridge that is allowed gives you roughly a centimetre into here. So it doesn't take much deflection of a piece of paper to actually change this length by a centimetre, and then it just drops off the test stand. So what you want to do is you want to make sure that the bridge is very rigid. Let's see if we can see some here. And there's another one. And again, the cylinders are nice and strong, but they're not connected to each other. There's that triangle. This is one where they've actually didn't even use triangles. They actually just used V-shaped pieces of paper looking down from the top. This one looks like this, which is nice. That's getting better. There's another one. These ones are kind of weak. I'm not sure. Don't do this. What's inside here? We don't know. So, as judges, you know, we're supposed to make sure there's no foreign material in there, nothing funny. So if we can't see in, we have to assume it's covered for a reason, that they're trying to hide something from us. Now, we know you students wouldn't do that, but don't make us think that they do. Yeah, you got a question there?
Yeah, is it okay if we have, like, we have the little doors that open so you guys can
Yeah,
look
you guys did
inside?
that, that was fine, yeah. And what you can do is, or you can just like cut a little inspection thing there so we can see in and see there's nothing in there except for the vanilla folder, that's fine. I still haven't seen the strong one yet. Oh, that's it. Alright, so the strong ones, you notice a lot of those bridges were very tall. Does height buy you anything in this thing?
Yeah.
No, because we can actually bring the test stand all the way down to here. So really, you know, your bridge only needs to be this big. And so all this is added, because we weigh the bridges too. And so it's a strength to weight ratio. So the taller it is, the heavier it is, no additional strength. You know, the force is going this way, there's nothing in that. So the strongest bridges you can make is, and also rather than having a single layer of large cylinders, how about having several layers, little teeny cylinders, all jammed together. So when you look at this bridge from the top down, it looks like, basically like honeycomb. And I just realized I had some packing material I meant to bring that we received this heavy piece of equipment, and it came in a cardboard case, a cardboard box. And at the bottom of the box, it was actually a layer of cardboard. It looked exactly like that, and inside was all hexagons, just like a honeycomb. But it was only about an inch high, but it was enough, and I stood on it. You know, it was about the size of half of this bench. Made of cardboard, it weighed less than a pound, and it could actually handle 300 or 400 pounds. So, and why it was so strong was because all the cylinders, or all the little hexagons were all joined to each other, and then the little tabs, they were all glued to the sheet above and below. And so when you start to stress this thing, there's nothing for anywhere to move. It's just like being in a crowded train, right? You want to get to the exit, you have to push somebody out of the way so you can move, right? So your bridge designed for these things, you know, just think of like a crowded room. You want to basically fill the space between the test hand supports with lots of things that are glued together, and that's going to be your strongest bridge. And also, make it about half an inch high. It doesn't have to be this big, long, tall thing. So, any questions on that? Any comments? Mineral mechanics is the hardest to make, I think, because you're basically having to make your own structure from flat sheet. And although using Elmer's glue again with the manila folders is very strong, because the cellulose fibers in the cardboard actually bond with the glue, the PVA glue that's in Elmer's glue. So it's a very strong joint that you make, but you have to give it time for the glue to dry. So make sure that 3 or 4 days. So if the kids are trying to make it on the night before MESA Day, it's not going to be dry by the time it comes to us.
How about curing possibility? I mean, like oven or something?
Time is good, but if you're a push for time, you can actually put it in an oven, a low oven, not 450, 200. The lowest setting where it says warm on the oven, you can do that and leave the door open a little bit and put it in there overnight, and that will actually dry the glue out nicely.
Also heat it up and then shut the door and like just sit.
Or you can do that too. Yeah. So let me go on to the last one, the bolted bridges. Actually, let me quickly go ahead. So you notice this maximum length is 45 centimeters for the bridge. And if we look at the dimensions of the test stand, it's 40 centimeters. So that's 2.5 centimeters on either side. So as I said, it's not going to take too much deflection of that flexible paper to actually decrease the length and drop off the test stand. So the only way to stop that flexing, and like I said, is to make a structure that's very strong and all glued together to its neighbors. Let's see. Materials, it's the same sort of thing, it's just manila folders. There isn't a maximum weight, I don't think, if I'm not mistaken. Most there is, 70 grams. So 70 grams is basically 2 folders plus a little bit of glue. The glue doesn't, the glue does actually weigh something. So, told not to go too crazy with that. Keep that in mind. You also have to have a way of measuring 70 grams. So I hope you all have like some sort of postal scale or something, access in your school in your science lab or something so you can weigh, because 70 grams is not very much, it's extremely light. And then that's pretty much it. There's very little restrictions on this competition, which is good. So, we move on. So there's a parcel scale down there which will take 450 pounds, and we have a little test plate there, and then we have a hydraulic car jack, and then when we crank the handle it pushes up the jack, and then it pushes down that arm, and it pushes down and transfers the force to the bridge, and then what we do is we actually weigh how many pounds of force is being applied. There's another shot of it. There's a shot of the car jack. And then we have a digital readout from the scale so we can actually see how many pounds is being applied. And then what we do during the testing, we have 2 people calling out the numbers, and then the highest number that anybody sees is the maximum load you get. And what usually happens is we keep testing until the numbers go up, and then you get a crack in the bridge somewhere, especially for the wood bridges. And then you keep on loading it, but usually after that first crack, then usually it just tends to go down. And when the numbers stop increasing, then we call it a quits on that one, and then we just pull out the maximum number. And then we calculate strength and weight based on that. Alright, so let's look at some bolted bridges.
One of the funnest things is about spaghetti competitions, the international spaghetti competition.